posted. Well, if 15 seconds won't feel like an eternity, I know that the last the last 2 minutes will. Okay, April, you ready?
Let's do it.
Okay.
Hi, everyone. Thank you for joining us for ASME's Tech Talks. These talks are a monthly one-hour webinar seminar and series that will focus on topical subject matter in a variety of mechanical engineering disciplines. It's represented by the ASME technical divisions and technology groups. I'm April Tone, Senior Manager of Technical and Engineering Communities at ASME, and I am joined here by the Robert Henry Thurston Lecture Award Committee Chair, Yu-Tai Lee, who will be moderating this Tech Talk. Before we get started, I'd like to let you know that you're able to send in some questions to be answered after the talk, but don't wait. You can always send in your questions throughout the presentation in the Q&A box located within your Zoom screen. And now I'll turn over things to Yu-Tai for further introductions.
Hello, everyone. Good day. Welcome to the 2021 Robert Henry Thurston Lecture. As you are probably aware that the Thurston Lecture Award is awarded to a leader in pure and or applied science or engineering to present to the society a lecture on a subject of broad interest to engineers. My name is Yu-Tai Lee. I am chairing the awards selecting committee. The committee has selected Professor Mary Cynthia Hipwell as the winner of the 2021 Thurston Lecture Award. Dr. Hipwell is currently the Oscar S. Watt Jr. 45 Chairs 2 in the J. Walker 66 Department of Mechanical Engineering at Texas A&M University. She received her bachelor degree from Rice University and her MS and PhD from the University of California, Berkeley. Upon graduation, she went to work at Seagate Technology Recording Head Division and later at Bula, North American Division. In 2017, she started her current position at Texas A&M. She is a member of National Academy of Engineering and a National Academy of Inventors Fellow. She has 16 patents and led the feasibility demonstration of many industry-leading technologies, including the transducer for the heat-assist magnetic recording (HAMR) technology, which she is going to share with us today. During the coronavirus pandemic, the Thurston Award Selecting Committee has selected the first Black awardee, Dr. Andrew Alling, in 2020, and also a first female recipient, Dr. Hipwell, for the 2021 award. To be noted that Dr. Hipwell's advisor at UC Berkeley, Chancellor Tian Changlin, was the winner of the Thurston Lecture Award in 1993. Unfortunately, he died at the age of 67. 28 years later, today, his student becomes the first female winner of the award. She has indicated that her lecture in narrow heat transfer technology is dedicated to honor her advisor's memory. Let's hear her lecture on heat assist magnetic recording, a narrow-scale heat transfer adventure.
Thank you for the kind introduction, Yutai. And I want to thank the entire award selection committee. It is a huge honor to be giving the ASME Robert Thurston Lecture this year. I'm going to be talking a little bit about heat-assisted magnetic recording and my nanoscale heat transfer adventure with that technology. Why am I talking about the nanoscale? Why don't I just talk about it as a heat transfer adventure? Part of it is because at the nanoscale, we approach a characteristic length of many physical phenomena. For example, the wavelength of light, the mean free path of gas molecules, electrical carriers and heat carriers, lattice periodicity or spacing for solids, and also there are a high percentage of atoms at the surface. So surface effects can become as significant or dominant to bulk effects. And this makes behavior and properties different than they are at the micro or even macro scale. And we can use this to enable new device behavior. This can also hinder device behavior, so we need to be careful about that as well. The origins of the nanoscale revolution are often brought back to Richard Feynman's There's Plenty of Room at the Bottom lecture in 1959. He gave this at Caltech to the American Physical Society, and it's really considered the first on atomic scale engineering. Feynman was a physicist, but was challenging colleagues to actually use some of the discovered phenomena to be able to engineer new devices. What's amazing about the lecture, which I highly recommend that you read, is that he predicts many of our modern technologies and their possibility based on nanoscale phenomena. While he may not call them the same thing I have them called or that we call them today, he describes each and every one of the technologies on this slide. More importantly, though, he challenges his colleagues to create the needed tools to be able to understand nanoscale structure and phenomena to the level to be able to engineer it. And so about 2 decades after that, the scanning tunneling microscope was invented at IBM. Its follow-on technology, the atomic force microscope, and in 1990, the near-field microscope, just to give you some examples of these created nanoscale tools. Having the nanoscale tools is really what broke open the nanoscale fields that followed on then in the 90s and in the decades to follow. About that same time, if you were attending the ASME Winter Annual Meeting, you probably attended the 1993 Robert Thurston Lecture, where my advisor, Chancellor Chang-Lin Tian, would have been talking about this recently emerging field of nanoscale heat transfer. He likely talked about some of his recent work in the area, but I am sure that, as he often did with his students, he challenged the audience to go to extremes. In this case, the extreme of the very small, and enter this new field. Recently, Ying Sun, Program Director of Thermal Transport Processes at NSF, compiled this history of nanoscale heat transfer research from that mid-80s until today. You'll see, similarly to what I mentioned with the history from Feynman's challenge, is some of the early work were creating the tools that were needed to do research in this area, and then many of the key discoveries over the last 3 decades. But what she's also highlighting here are some of the important commercialized technologies only possible because of some of this research in our community. And I'll be talking a little bit more about heat-assisted magnetic recording in particular today. I do want to give a note of special thanks to Seagate Technology, and in particular my colleagues, Dr. Tim Rausch, Mike Kotsky, and Neil Zuckerman, for sharing some of their previously publicly presented hammer slides with me. When you leave a company, you don't take anything with you. And so it's only because of their generosity of sharing some of this material about the work that we did at that time that I'm able to share that with you today. So first, just want to introduce the hard disk drive, get you a little bit familiar with that, so some of our terms won't be so foreign. First is just the disk, or we'll also be referring to it as the media where the data is stored, and the recording head here. And some things that you'll notice is there's a lot of dimensions that are very small, such as the spacing between the head and the disk, which is only 2 nanometers. Considering that a human hair is 70,000 nanometers, this is very, very small. The writer is very small. The spacing on track that we need to be able to control the on-track performance too is very small. And so there's already a lot of nanoscale engineering even before heat-assisted magnetic recording is brought in into the challenge of the disk drive. And one of the key parameters for the hard disk drive is areal density, or the number of bits that can be stored in 1 square inch of disk or media space. Also, to help you become a little more familiar with the recording head, this is the view if you were looking up from the disk to the head. You would see this little slider, this little brick slider, which actually is the substrate on which all of the electronics are built up in this direction. So this is where the read and write transducers are, and bond pads that electrically connect the head into the drive. The gimbal and suspension allow preload and pitch and roll of the head as it's flying on that air bearing over the disk. As I mentioned, the most important parameter is areal density, and you can see 9 orders of magnitude in improvement in areal density since the first disk drive in 1956. So this level of improvement is actually many times more aggressive than the more well-known Moore's law, which is the scaling of the number of devices on an integrated circuit chip. And the reason that the disk drive industry has been willing to invest so much in technology is that it really drives the economics of the business. Higher areal density certainly enables new capacity points, so you can sell say a 20 terabyte drive instead of a 16 terabyte drive, but also cost reduction. So for a 2 terabyte drive, can potentially ship it with 1 less disk and 2 less heads, takes a lot of cost out of the drive. And so areal density is really the way that the business keeps going forward, and the economics drive this need for continued technology improvement. What's been the challenge for magnetic recording is really this scaling that needs to happen in the disk. So this is the recording, the little track of recording media. We have the 2 blue and white indicate 2 different magnetizations. So let's just say that blue is south to north up, and white might be south to north magnetization down. And the drive is actually detecting the absence or presence of transitions between the 2 magnetizations. And so as we make the track smaller, if we don't make the grain smaller, you can see that this transition relatively becomes wavier and wavier, and that would actually contribute to noise. And so to be able to keep the signal to noise constant, we actually, as we scale down the bit, need to scale down the grain. The problem with this is that if we look at the time, the energy and the time to be able to randomly cause a bit to flip its, or a grain to flip its magnetization, this could just be caused by the thermal energy at room temperature. You want grains to not be flipping very often. If this is somebody's bank account zero or picture of their child, you want these grains to be very stable. And so this time in between events at which you have a probability of a random flip, we want it to be very, very long. And so we want this number to be big, and we want it to stay constant over time. And so as you scale the grain down, scaling down the volume, this is related, exponentially to the volume and this resistance to flipping the magnetization. And so as we make the volume of the grain smaller, we need to increase that resistance to flipping the magnetization. But the problem is, as we do that, it actually is also the resistance to changing the magnetization with the writer's field. And so it makes it more and more difficult to write. In fact, may get to the point where it's beyond where we have enough field to be able to write. And so that's the concept of hammer, heat-assisted magnetic recording, is where you take a disc or medium, and it can be very high coercivity. And coercivity is that resistance to changing the magnetization at your normal room temperature. And this is our amount of head field. So we can't write while we've got this resistance that's very high. But if you heat the media to a temperature called the Curie temperature, the coercivity actually drops quite dramatically down to a level where you would be able to write. Then you can actually cool it back off, back to room temperature, and the bits, again, and grains are very stable at that temperature. So in a sense, you can only write where the disk is hot. And so this is actually one of my favorite parts of the story, is because the bit can actually, its size can actually be determined by the heated spot. So you can actually have a larger magnetic write bubble, but you only write where the disk is hot. So that optical heated spot can determine the size of the bit. And so this puts us heat transfer engineers in charge of the write process, which is very exciting, but it also gives us some big responsibility here, because we need to figure out a localized heat source. And by localized, I'm talking about 50 nanometers, so an extremely, extremely small spot. And that spot needs to be immediately adjacent to where the writer is creating the magnetic field to be able to change the magnetization. And so this is now a pretty big challenge for us heat transfer engineers. So first we might just say, let's just take a laser, focus it down to a small spot. We can use that laser to heat the disk. And we run into a problem called the diffraction limit. And due to the wave nature of light, light can only be focused down to about half its wavelength, and that's called the diffraction limit. And so if we think about practical wavelengths of lasers, we're still talking hundreds of nanometers. And so if you look at an example of one of the smallest wavelength lasers in a practical commercial sense, which is a Blu-ray drive, that's about 402 nanometers. And so with again, a practical numerical aperture, we're talking about a spot size of 238 nanometers, which is small and impressive, but with today's definition of the track pitch and the bit size, this is huge. This is much bigger than our 50 nanometer spot. And so we cannot simply just focus laser light with conventional optics to be able to create this small heated spot. So we might just look at an aperture. Can we block the rest of the light and only let 50 nanometers through? But if we look at the mathematics of that, we look at the amount of light that's transmitted, it's related to the radius of that hole to the fourth power. So if we're going to start scaling this type of technology, and I want to increase the areal density, so I want to make that hole smaller, if I make it smaller by just a factor of 2, I would need 16 times more power to get the same amount of light through. And so this just isn't a practical solution. You'd need too much power as you try to go to higher areal density. And not just that power is wasted, but also that power you're not using is going to translate into heat in the head, which also could cause reliability problems. So this is not a solution for us either. So in 1998, Thomas Ebsen actually discovered you could get more transmission than what would normally come through an aperture with surface plasmons. And so he had a silver film and it had 150 nanometer holes in it. And the whole area would have predicted about a 5% throughput. There was 5% area coming through, but he was actually able to almost double that with a 9% throughput. And so how did he do that? He did that with surface plasmons. So this is both one of those small scale effects and it's a surface effect. And so if we have our little silver film here and light interacts with that film, electrons, it interacts with the electrons and the charge is displaced. When the charge is displaced, the positive charge actually tries to pull it back and you start to get charge density oscillations. The charge density oscillations and their associated electromagnetic field due to the charge movement are called surface plasmon polariton waves, or we'll just call them surface plasmons for short. And they actually create this electromagnetic field as a near field. So you can see the decay of that field here. It's not a propagating field. That field is only present within tens of nanometers of that surface. And so the field is only going to be active when we're very, very close to the surface of that material. And so people had known about surface plasmons since the 1950s, but Ebsen was really the one to show that you could do something useful with it. shine light onto one of these plasmonic materials, convert it into a surface plasmon, and then it would pass through the hole and convert it back into a photon and emit more light than was expected. And this had been used for many centuries. Small metallic particles in glass actually had different effects on the transmission and reflection of light, and were used have been used for centuries. But what if instead of taking glass with a small gold sphere, we actually just took one gold sphere, just one sphere, a couple 100 nanometers, and focus light on it. If we look at those wavelength of light and the interaction with this gold sphere, at certain wavelengths, you can get very, very efficient coupling into that gold sphere. And you can see the electromagnetic field then around the gold sphere. So we've got this efficient coupling of the light into the sphere. Can we use those surface plasmons on the surface to be able to transmit energy into disk? What if we put disk media really close to that sphere? And we can see that we can actually get a lot of the energy from the laser coupled into the disk and now into the media. But it's still not very confined. This is still about 100 nanometers in width. And so it's still not, it's smaller than focusing it, but it's not as small as we want. So what about the solution of actually putting a small peg at that surface? This is now a 50 nanometer peg. The surface plasmons only interact at the tip of that peg, and we can get a very small spot. And this is the work from Seagate Research Pittsburgh, published by Bill Challenger and teammates in 2009. And this is often called the lollipop design. And so you put that all together, you have the light focused onto a gold disk that interacts with the electrons, creates surface plasmons that travel along the surface down to the peg. At that surface, the electromagnetic field, or the near field from the surface plasmons, can create a current in the media and heat that very small spot, just where that near field is interacting with the disk. And this is a much smaller spot than we could create if we tried to focus that laser light onto the disk. So how you actually integrate that into a head. This is our friend the slider that we saw earlier. Actually mount a laser on a submount on that head, couple the light into the head and through a waveguide and mirrors. It's focused onto the near field transducer that we see here, that we need to get in very close proximity to the disk. As far as how this is integrated with the rest of the head, this is a side slice of the head. That waveguide is here. The near field transducer is very small at the bottom. It's put in close proximity to a right pole, so the magnetic field and the heated spot are very much in alignment. If we look at that from that surface, so in this direction, looking at that up from the disk, you just see that square end of the peg, and it's very close to the right pole. So again, we have magnetic field and heated spot very close to each other. And at a little bit larger scale, although this is still all very small, again, you can see the slider with the submount and the laser integrated onto the head. So we're using small scale, near field effects to be able to create a very small spot. Heat transfer engineers are in charge of the world, but with power becomes a lot of responsibility. There's near field transducers, or we'll just call them NFTs, are gold-based, surrounded by a dielectric. There are a lot of losses. It's not perfect coupling, so there are a lot of absorptive losses in the NFT, as well as in different parts of the head. And the temperature there can get very, very high. It's a very high energy density. Looking at that original lollipop design before we did all the nanoscale heat transfer magic with it, if we compare, this is a review article from Eric Pop that talked about densities in the chip industry. And if we look at kind of where IC power densities had been increasing and kind of plateaued off in the 2000s, that was at 100 watts per centimeter squared. He mentions that the surface of the sun is 6,000 watts per centimeter squared. To give you an idea of the heat transfer challenges that we had looking at HAMR, the original HAMR NFT was 40 million watts per centimeter squared. You know, when someone's talking about the surface of the sun in a reliability presentation, it's probably not good. And particularly if you're higher than that, it wasn't because the laser powers were so high, we're talking about tens of milliwatts. It's that the size of that peg is so incredibly small, a 40 to 50 nanometer square peg. It's a really, really small area. And so it's a moderate amount of energy in a very, very small space, giving a very high density that needed to be dealt with. And so first was just getting some of that heat out. And so we have the NFT, and the writer, the right pole and the rest of the writer is actually a very, very large piece of metal compared to the very small NFT. So the first thing is to thermally connect up the near field transducer to the right pole with the heat sink. And the other was to be able to slope the pole and get it out of the way of the optical path. So we aren't getting much of that scattered unused light onto the right pole. Those two things made quite a bit of difference in improving the temperature distribution. But we also had to consider nanoscale effects, because this device, as we've already shown, the disk is 200 nanometers, the peg is 50 nanometers. It's very small. We need to be considering nanoscale effects. So this is from a presentation that Neil Zuckerman gave at the 2013 ASME Heat Transfer Conference, talking about some of the important nanoscale effects in HAMR that can't be ignored. One of them is looking at the interface resistances. And this is important when surfaces are important. And the lattice vibrations, the frequencies that can be supported in the structure of the metal are different than those can be supported in the dielectric. And so when you have those lattice vibrations trying to transmit the heat from the metal to the dielectric, it's really an acoustic impedance mismatch. And so some of those frequencies will not be able to transmit into the dielectric and will reflect back into the metal. So that actually restricts heat conduction out of the metal into the dielectric. And this is going to be a challenge for us in trying to cool that lollipop. We also have to be considering the carrier temperature mismatch. So when the disk is actually, all the electrons are what are going to be absorbing the energy from the laser, interacting with the laser. And they will actually, it takes them time, when we're talking about a very short time scale here, it takes time for them to actually interact with the lattice and give their energy off to become heat in the lattice. And so the temperature of the electrons is actually going to be different for the time scale that we're talking about from the lattice vibrations or the phonons. And so we have to consider the different temperature between the electrons and the phonons or lattice vibrations in the device. And then while these electrons have a different temperature than the lattice, they're called hot electrons, and they can actually travel about 100 nanometers before they end up interacting with either another electron or the lattice. And so this is actually fairly efficient transport across that length. And so This is actually a positive effect because those hot electrons can transfer some of that energy away from the PEG. And this actually has the effect of cooling the device, or at least the PEG. It gets some of the energy out into the disk instead of all staying in that localized PEG area. And so all of these, we'll see how much of an effect they have in the next slide, but these are effects that happen only because we're at these very short time and length scales, but they have a material impact on the temperature of the device. So if we look at the device and aren't considering any nanoscale effects, at least in this situation, we're predicting a phonon or lattice temperature of about 530 C. And that's the temperature that's going to determine the reliability of the device. If we consider all of the nanoscale effects, the phonon temperature ends up higher at about 565 degrees C. And so that can be a material difference in bringing down temperature-driven failure modes or being able to accurately predict them. Just to kind of see the magnitude of the individual effects themselves, some of it is that the ballistic transport is offsetting some of the interface resistance, but that's not going to always be the case, and we need to be looking at the relative magnitude of both of those effects. See here, if we don't have that ballistic hot electron transport where it's the electrons are transporting in about 100 nanometers before they interact, you would actually predict to be about 605 C. So that's where those hot electrons actually are helping us cool the device. If we didn't have that interface resistance where the difference in the lattice vibration frequencies of the metal compared to the dielectric are restricting that heat coming out, if we didn't have that effect, then we would actually be down at 470 C. And so accurately including these nanoscale effects are very important, both for accurate prediction of the temperature, but also when we're identifying the mechanism or possible solutions that might be able to help us cool the device, such as potentially trying to better match the impedance to be able to have better conduction out. As an example, being able to accurately model these effects is incredibly important to be able to optimize the device and make it reliable. It's also important to be able to engineer the media and the thermal performance of the media. They had to engineer the lubricant, the overcoat, the new recording layer, an interlayer that controls the direction and speed of the heat transfer, a heat sink to get the heat away, and a substrate that could actually handle that heat. Controlling this thermal profile and therefore the size of the bit really in the recording process, the design of the media and the nanoscale heat transfer design of the media is very important. So when we have that near field interacting with the media and creating the small heated spot, we want that spot to get heated quickly and then be able to have that heat flow down and away so that by the time the disk rotates around again, the spot is no longer hot. Otherwise, the right field will write over it again and erase it. So we want to be able to get that cooled quickly within a revolution, but not so quickly that you have to keep dumping more and more laser power in. So that balance is important. We also do not want good lateral conduction. We do not want it to conduct laterally because that will actually spread the spot or erase other data that we might have on the disk. We also want it to come down and away, but we do not want this heat sink when it becomes hot to conduct the heat back up into the recording layer, because that will also erase data. And so this is a challenge directionally, anisotropic properties, and really is a difficult balance and challenging using nanoscale heat transfer effects to be able to control a lot of those properties. We also had to consider some nanoscale reliability effects, and this example is our early primary failure mode, which was PEG recession. And this is a transmission electron microscope image and then movie of the lollipop as it's ramped from 40 to 400 C over about a 15-minute time period. And it will show you some of the mechanisms of failure and what's going on in the head. So, oops, sorry about that. We'll try that again. So you will see grains growing in the PEG, in the disc, and also the gold is densifying. And as the gold densifies, it wants to pull the PEG back into the disc. And you can see the PEG pulling away from the surface and being pulled into that disc. And because the surface plasmon effect is only a near field effect, once this PEG has retreated from the head surface, it is no longer within that tens of nanometers of the disc media, and the near field cannot reach the media anymore, and it fails to write any further. It's not heating that spot anymore. And this movie, really, with the tools of nanoscale technology, a transmission electron microscope, we are able to study this mechanism and come up with what was going on in this failure mode. We also had to bring in some of the other reliability issues that people were seeing with nanoscale gold and kind of different behavior, because at this 400 C, gold should not be melting. So what's happening with these phenomena? And so we're seeing grain growth, which is certainly one of the problems we were having. People were seeing poor adhesion to oxides for these thin gold films. And with nanoscale gold structures, people were seeing nanoscale structure instabilities. And some of this is with everything being a surface, those sharp corners, it's easier for atoms at those corners to be pulled off or to minimize energy in those rounder shapes. And so these slides are actually from my colleague, Mike Kotsky, who and his team in my group that actually worked on figuring out this mechanism and coming up with material solutions. And so by studying these mechanisms, as well as what had been going on in literature, we're able to put together what was going on, both that densification, the stresses, what was being allowed with the diffusion at the surfaces, and to be able to come up with a solution. So the solution was really looking at both reducing the temperature and material improvement. So if we look at this reliability, trying to get to higher hours of lifetime versus temperature, both created materials that had better lifetime at a given temperature and things to reduce the temperature, both of those approaches to get us to higher lifetime. And so in temperature reduction, that heat sinking, reducing the amount of light that was interacting with other parts of the head. In the materials case, looking at things like gold that held its grain structure, dense gold that was already densified, ultra-thin adhesives that would prevent that pulling away and hold the head in place, as well as some chemical interactions at the interface. All of these put together to be able to increase the reliability. So this led to all of these things together, led to a lot of reliability improvements, including getting to this 1,000 power an hours. And this is actually a demonstration that was publicly announced from the Drive Center with some of the heads of some of our collaborators at the 2014 Magnetic Recording Conference. And this was exciting because it was a very practical amount of power and hours. And so between the practical reliability hours and the practical areal density hours, really were able to establish feasibility of the HAMR technology. So this is a movie of a HAMR drive with a clear cover. You can tell it's HAMR because there you can see the light scattering off the disk. That early nanoscale heat transfer work was incredibly important to establish HAMR feasibility in 2015. That is what enabled Seagate to be able to transfer the technology to the product teams that then really increased the full population of heads, median drives to be able to be at shipping product levels. Seagate's announced that it's currently shipping 20 terabyte HAMR drives in volume today, and will ship a 50 terabyte HAMR drive in 2026. What am I doing today? I joined Texas A&M in 2017 and started the Invent Lab. I've pivoted a little bit from the head disk interface to the finger device interface and looking at the thermal and tribology interactions for haptics, for robotic interactions and small scale and soft devices, and brought in some other researchers kind of in a research cluster to be looking at these key areas. We're also teaching innovation classes and workshops based on some of the things that we did at Seagate to be able to improve our innovation. In addition to my Seagate colleagues, I do want to acknowledge my students and colleagues in the Invent Lab, as well as our financial supporters. And I'll now be open for any questions you may have about HAMR. Thank you.
Great lecture. Thank you very much, Cynthia. I hope everyone in the audience enjoy as much as I did. And this is a great lecture. This award also comes with a certificate, as you see in the screen, for Dr. Hipwell, and also come with a check. Both items were mailed to you, Cynthia. So expecting sometime next week or week after.
Thank you very much. A huge honor.
Thank you. And now we can actually start with the Q&A. Let me check if we have any Q&A. Right now we don't have any, but please tell. This, we have to wrap up the Q&A section. Now we turn back to April for her final conclusion.
Thank you. That was fantastic. It was a great conversation. Before we wrap up, I'd like to mention that if you're interested in obtaining PDF certificate or would like to request the Tech Talk topic, look out for an email coming from ASME. If you've opted in, you will receive it soon. Also, if you have colleagues that were unable to join today for this Tech Talk, it will be posted within the ASME members page for Tech Talk series. It takes about 1 to 3 days, but it'll be there very soon. Our next Tech Talk will be discussing digitization on Thursday, February 17th at 12 p.m. Eastern Time. Additionally, if you're an ASME member and would like to join a division, visit asme.org and log into your account. Click on additional info, and there you'll be able to select up to 5 areas of interest by clicking edit next to the technical division interest area. By doing so, you will become a member of those entities. Thanks again to everyone for joining us today. We certainly hope to see you again soon. Bye-bye for now.